Okay, Assalamu alaikum. Let's resume our discussion. Fortunately, the power is back. It's 12:25. Okay, we might be a little late, but you will get this video recording for today's class, and I hope it will help. So we were discussing the ASCII code, and I guess we were done with the discussion of ASCII code. The ASCII code, like the one that we are currently using, it is an 8-bit code. So it is an 8-bit code. That means uh, let me get the pen. So we have 2 raised to the power 8 possible combinations. Okay, that is 256 possible combinations. So the most that we can represent with an ASCII code is 256 alphanumeric characters. Now it may be enough for some languages, but if you want to encode all the languages in the world, this is definitely not enough. I guess we mentioned in the class that even the Chinese language Mandarin, so it has around say 13,000 characters. Okay, so we cannot use ASCII to encode all those different characters. We need a bigger code, and hence we have this other code called the Unicode. So the Unicode extends ASCII, Unicode or Universal Code. Okay, we'll just briefly mention it. It extends ASCII to 2 raised to the power 16 universal character codes, which is 65,536. Okay, so it is enough for encoding all the characters in all languages in the world. And many modern applications like Microsoft Word or PowerPoint or any other applications that you're using nowadays. So they provide support for Unicode. Okay, so you can use Unicode encoding in those applications. Okay, so Unicode uses basically 2 bytes or 16 bits to encode a single character. So it has 16-bit code words, and one code word is used to encode just one character. Okay, so this is enough. If you want to know about more about Unicode, I guess there is a little material in the textbook, and you can also go online and check further details. Okay. Now, as far as this discussion is concerned, we have talked a lot about binary and binary addition, multiplication, and subtraction, and all that. What we have not covered yet, one thing that we have not covered yet is the binary representation of signed numbers. Okay, so signed numbers like positive and negative integers, and signed number arithmetic. Okay, so the arithmetic, the addition, subtraction, or subtraction of signed numbers, we have not covered that. So that will be the subject of our next lecture. But in this lecture, this is as far as we'll go regarding numbers and codes and all that, binary numbers and codes and all that. And in the next lecture, in the next part, the remaining part of this lecture, most of the material that we will be discussing, we have actually talked about it in our first lab session. So we'll talk about binary logic and gates. We have talked about these things. Binary variables are variables that take on one of two values. Okay, so we call those values as true or false, 1 or 0, high, low, um, on, off. So we can name them, we can call them different names, but they are all binary variables. They have these two possible values. We talked about logical operators. Logical operators basically operate on binary values or binary variables. Okay, so logical operators, they operate on binary values or binary variables like true and false, 1 or 0, and all that. We talked about the fundamental logic operations or logical operators. Those are AND, the logical OR, and the logical NOT. So these are the fundamental logic functions. Okay, these are the basic logic functions or operators. And then we can have more operations which are going to be combinations of these operations. Logic gates are basically electronic circuits that implement logic functions. So we can have an AND gate that would implement the AND logic function. We can have an OR gate that would implement the OR logic function. We can have a NOT gate that would implement the NOT logic function. And similarly, we can have other gates. We talked about the NAND gate and the NOR gate, the exclusive OR gate, the exclusive NOR gate. We talked about all those gates. So the NAND gate is basically not of AND. It implements like a composite function. It is the not of AND. You first take the AND of the inputs and then you invert the output. That is what NAND is. Similarly, the NOR gate is also a composite function. It implements the not of OR. You first take the OR of the inputs and then you take the NOT. The exclusive OR is different. We talked about it before. So if you have odd number of inputs at um, odd number of ones in the input, the output would be 1. Otherwise, it will be 0. The exclusive NOR is exactly the opposite of that. So logic gates are basically electronic circuits that implement logic functions. And these are logic functions. The electronic circuit that implements the AND logic function is called an AND gate. The one that implements the OR logic function is called an OR gate, NOT gate. Okay, so this you should know these terms. You should be comfortable with these terms. We also talked about Boolean algebra. So Boolean algebra is concerned with logic functions or functions which evaluate to either 1 or zeros, and those functions are functions of binary variables. Okay, so Boolean algebra is concerned with these things. Why do we need to study or understand Boolean algebra? Because it forms the basis or foundation of digital systems. If you need to analyze or design digital systems, you need to have a good solid understanding of Boolean algebra. Binary variables, again, we said that they can have two binary values. We can call those values as true, false, on, off, yes, no, 1, 0, high, low. You can name them. Okay, doesn't matter. Here in this course, we will use the value 1 and 0 to denote those two values. We will not be using yes, no, on, off, or true. We can call them, but when we are evaluating, we'll be mostly using 1 and 0. Okay. How do we identify Boolean variables? Like what symbols can we use to identify them? So you can use capital symbols, you can use capital letters, small letters, you can use letters with subscripts. You can use words as well, reset or start. So later on, we'll be using sequential logic circuits. So you'll come across such inputs as reset or start it or add one or whatever. So we'll come across these all these identifiers. So these are all valid identifiers. Okay. When we'll be using Boolean expressions or functions in Boolean algebra, mostly we'll be using notations like these single letter notations. They can have subscripts. Later on, when we are designing digital circuits, so then you can come across inputs like these. Okay, so they're more meaningful. They basically tell you the purpose of this particular input. So say it will reset something. So if it is a counter, it may reset the counter to the value 0. If it is a CPU, it will reset the CPU, restart. So basically restart means that the program counter or the register in the CPU which holds the address of the instruction which has to be executed next, it is reset to 0 or some initial value. Okay, that is what reset means. Okay, so basically this is like before we start Boolean algebra and we go into the details of combinational logic design and all that, these are the terms that you should know. That's why we are basically going through these. This is introductory material. This is also part of chapter 1. So again, we have talked about these basic operations, and or not. We have also talked about how do we denote and. So it is denoted by a dot or the absence of a dot. For example, if we have z, the variable z, which is equal to the and of x and y, so we can write it either as x and y, or we can put a dot here, x dot, so x and y. Whether there is a dot or whether there isn't a dot, this basically shows a logical and. It is not x multiplied by y. It is a logical product. We will later call it as a logical product, not just an arithmetic product. It's not an arithmetic product. It can be called a logical product, but this is how we represent the AND operation. Similarly, OR is denoted by this plus sign. Okay, so if we say z is equal to x or y, if we want to write this Boolean expression, this is a Boolean expression. We can write it like this: z is equal to x or y. We will not read it as x plus y. It is not x plus y. It is not arithmetic addition. Okay. Not is denoted by an overbar. For example, if z is the invert of the inversion or inverted output of x, so we can write it as z is equal to x bar, or we can write it as z is equal to x dash or x prime, single quote, or we can use the tilde character. This is a tilde character. We can use it before x. So this also represents a complement operation, a bitwise complement operation, or a not operation where 1 is turned into a 0 or 0 is turned into a 1. Okay, so all these are valid expressions. This is again a repeat. We have talked about this in our first lab session. Okay, in fact we talked about more logical operations. We talked about NAND, which was not of AND. We talked about NOR, which was not of OR. So I hope you all know and remember that, and in fact you verified the truth tables of all these logic functions. Similarly, we also talked about exclusive OR and exclusive NOR. So as an exercise, you can recall all these operations. Okay. This is the notation. Again, why we gave these examples there. Y is equal to A and B. You have to read it as this. Y is equal to A and B. Z is equal to X or Y. X is equal to not of A. Okay, this is how we read it. And again, this statement 1 plus 1 is equal to 2, and this statement 1 or 1 is equal to 1, they are completely different. This is an arithmetic expression, and this is a Boolean expression. Both are true, okay? But this operation and this operation, these are different operations. They use the same symbol, but these operations are different, and this is how you read it, okay? This is 1 or 1. 1 or 1 is equal to 1. And this is 1 plus 1 is equal to 2. So this is arithmetic, this is logical. So notation, you should know the notation and you should be careful with the notation. You should not get confused with it. Okay, operations are defined on the values 0 and 1 for each operator. So say for example, let us look at this expression. Y is equal to A and B. So if this operation has to be defined for each possible value of A and B. Okay, so A and B are binary variables. They can both have 0 and 1. So A can be 0, B can be 0, A can be 0, B can be 1, A can be 1, B can be 0, and both A and B can be 1. So when we want to evaluate this operation, we have to evaluate for their values. Okay, so operations are defined on the values 0 and 1 for each operator and operand. So this is AND. For each, what is AND? AND is basically if any of the input is 0, the output is 0. That is AND operation. So here both inputs are 0, output is 0. Here this one is 0, it drives output to 0. Here this one is 0, it drives output to 0. And both are 1 only, then the output is 1. This is OR. When any input is 1, the output is 1. Okay. So here this one is 1, so it drives the output to 1. Here this one is 1, so output is 1. Here both are 1, so output is 1. The output is only 0 only if both the inputs are 0. Okay, and not is easy. So the not of 0 is 1 and the not of 1 is 0. This is simply inversion. You flip the bits, okay, make 1 0 or 0 1. That is what not operation is. We talked about the truth table as well. So what is the truth table? It is a tabular listing of the values of a function for all possible combinations of values on its arguments. So arguments are inputs. So if you have any function and you write down all the values of that function for all possible combinations of its arguments or inputs, that is a truth table. So this is the truth table for the logical AND operation. Okay, and this is a here this AND function is a two variable AND function. We can find a three variable AND function as well. So these are the possible values for these two variables 0 0 0 1 1 0 1 1, and these are the possible values of the output. So we have gone through this. We don't need to spend a lot of time here. So this is the truth table for AND. This is the truth table for OR. OR. So this is OR is this function. So what is the value of this function? And it is a function of like z here is a function of x and y. Z Here is a Boolean function of x and y. So you can think of x and y as its arguments. X and y are its arguments. Okay. So or its inputs. So what are all the possible combinations or values of x and y? So these are all the possible values of x and y. And what is the output of the function for each possible combination? These are the output values of the function for each possible combination. Okay. So this is a truth table which lists all the possible values of a Boolean function for all the possible combinations of its arguments or inputs. And similarly, this is the not function. Okay. Now, again, we will go into a lot of detail about this implementation, but this is just the introduction. Okay. So this part is also covered in your chapter first of your book. So how do we implement these logic functions? So we implement these logic functions using electronic circuits, and those electronic circuits are called gates, and those electronic circuits are made up of transistors. And in digital design and digital logic, we use the transistors as switches. We don't use them as amplifiers. Okay. So here, like, we'll draw some simple circuits where there are literally switches or buttons, and we can show that those buttons, they will operate as like, using those buttons we can implement these simple logic functions. Okay, the and function, the or function, and the not function. So we'll see that when how are we going to interpret the status of the switches. If the switch is closed, it is conducting, we say it is logic, it represents logic 1. When the switch is open, it is, and it is not conducting, we say it is logic 0. The output is going to be a light. When it is on, it is logic 1. When it is off, it is logic 0. Not uses a switch such that logic 1 is switch open when it is not conducting. It is opposite to this thing. And logic 0 is switch closed. Again, this is kind of a trick. Okay. Um, like, many of you may not be convinced with this interpretation, but in any case, it doesn't like, it matters that you are convinced or not. But this example, it is it if it does not make a lot of sense to you, in two cases it will make, in the other case it may not. So it doesn't matter, don't worry about that. So I guess you know these circuits. So this is a simple electric circuit. This is a voltage source, and these are two parallel paths, and this is a light. So this light bulb will turn on if either of these switches on. If we turn on this switch or close this switch, so the light bulb will on. If we turn on this switch, the light bulb will on. If both are turned on, it will be on. The light will stay off only if both switches are off. Okay, so this is an OR gate. When you arrange these switches in parallel, you actually create an OR gate. Okay, so both these switches must be must be off if you want the light to stay off. If either of these is on, the light will on. Then we have the AND gate. So these are basically switches in series. The light will turn on only if these two switches are on. If these are closed, okay? Only then will it turn on. So this is the AND gate. So if these are not turned on, then it will remain off. This is the NOT gate. Again, in the NOT gate, we are just playing a small trick. Like, if the switch is closed, we say that the closed switch represents a logic 0. So when the switch is closed, we say it represents the logic 0, and then the light will be on. We say it is logic 1. And when the switch is open, we say it represents logic 1, and then the light will be off, which represents logic 0. So it is kind of tricky. आप कह रहे होंगे कि जी ये तो आपने धोखा दिया हमें, तो हाँ, ये फील होता है कि ये धोखा है, but that is the example of NOT gate. ठीक है? This is how we explain NOT operation. Now we can go for another function, and we can use these switches to implement this other function. Now if you look here, यहाँ पे this is parallel path, this is parallel path, तो इन दोनों का तो OR हो रहा है. These two are in series, so these are ANDed, and similarly this thing is in series with both these, so this is also AND. So इन दोनों का AND हो रहा है. ये कौन से हैं? ये B और C prime. इन दोनों को हम एंड कर रहे हैं, इफ़ यू लुक एट दिस सर्किट। फिर इनको हम और कर रहे हैं विद डी, ठीक है, ये दोनों पैरेलल में लगे हुए हैं, तो हम इनको और कर रहे हैं, ठीक है। अच्छा, और फिर ये जो दोनों का कॉम्बिनेशन है ये एंड हो रहा है विद ए, ठीक है, ये एंड हो रहा है विद ए। अच्छा, तो ये लाइट कब ऑन होगा? इस लाइट के ऑन होने के लिए ए का ऑन होना ज़रूरी है बेहद, बिकॉज ए इज़ बीइंग एंडेड विद दिस थिंग। और इन दोनों में से किसी एक का ऑन होना, या डी ऑन हो या बी और सी बार, ये दोनों ऑन हो, ठीक है, या ये चीज़ ऑन हो, वन हो, या ये चीज़ वन हो, ठीक है। और इसका तो वन होना हर हाल में ज़रूरी है अगर हम चाहते हैं कि ये वन हो, ठीक, सही है। अच्छा जी, आ, इस एक्सप्रेशन को हम यूं भी एक्सपैंड कर सकते हैं, लाइक नॉर्मली तो हम, अगर आप देखें ना, नॉर्मल जो अरिथमेटिक हम करते हैं उसमें हम इसको मल्टीप्लाई करते हैं, यानी ये डिस्ट्रीब्यूटिव लॉ हम अप्लाई कर देते हैं। तो दिस इज मल्टीप्लिकेशन एंड हेयर वी हैव एडिशन, ठीक है। अगर हम ये नॉर्मल अरिथमेटिक एक्सप्रेशन इसको देखें तो मल्टीप्लिकेशन इज डिस्ट्रीब्यूटेड ओवर एडिशन। Here we have or inside the brackets and outside we are ANDing it. So AND is also distributed over the OR operation. So we can write it as AD or ABC bar. So we can write it this way as well. Okay. Now either this thing needs to be 1 or this whole thing needs to be 1 in order for the light to turn on. Both, in both cases A शामिल है, ठीक है। So या तो आप A को, you can take out A, you can simplify it like this, D or again वो जो original form है ये वाली, or you can go with this one, doesn't matter, ठीक है। But this is just an example के now you have a circuit and then you, if you want to know के which boolean function is it implementing, ठीक है। So you can learn that. Acha. So this is basically just introduction. Like we'll be going through a lot of detail, and we won't be using these electric circuits or relay circuits in order to implement logic functions. We'll be using logic gates, but this is just to give you an example कि ये हो क्या रहा है, ठीक है? Now, in the earliest computers, logic gates again, they form the basis of modern computers. So earlier computers में relays were used, ठीक है? Relays basically they acted as switches, and they acted as switches. They had these energizing coils. I don't know whether physics में आपने ये चीज़ पढ़ी थी या नहीं, वो electric bell वाली मिसाल, ठीक है? So the electric bell has this energizing coil. When somebody presses the bell's button, so the coil is energized, and uh, say this hammer, it starts hitting the bell, ठीक है। And when it hits the bell, so वहाँ पे circuit टूट जाता है से, and then the coil is de-energized, और ये spring loaded होता है, तो it returns back, फिर वहाँ circuit बन जाता है if the button is on. So it goes on and on like that. So relays have this magnetic coil which, when energized, they make a circuit, and which are when they are de-energized, they break a circuit, something like that, ठीक है। This is how relays work. So earliest computers had these relays, and those relays were switches, ठीक है। तो इन सब में अगर आप देखें ना, जो कॉमन बात है कि तमाम computers were based on binary logic. They all used different ways to represent ones and zeros. They were all based on Boolean algebra. Okay, so Boolean algebra is important. Binary systems is important. Earlier computers used relays to represent as switches to represent those ones and zeros. Then came the vacuum tubes. Okay, they were used instead of relays again to as switches to represent ones and zeros. And then came transistors, and right now we are working with transistors, and transistors are used as switches. So, and there are billions of transistors that are used as switches. So the other day I was just looking up the Apple M1 chip. Okay, so it is basically a system on a chip, SoC, systems on a chip. So the M1 is not just a microprocessor, it has plenty of different chips on a single chip. And you would be amazed that it has around 16 billion transistors. The Apple M1 chip has around 16 billion transistors on a single chip. Okay, so that is the number of switches that are being put together in order to make something as complex and powerful as the Apple M1 chip. So you can look it up. So right now we are using these transistors as switches, and they form the basis of structure and functional basis of all digital devices. We learned about these symbols. I hope you remember that, and we added some extra symbols, the NAND as well. So this is the AND symbol. This is the AND gate. This is the symbol for the electronic circuit that implements the AND logic function. These are the inputs. This is the output. Okay, and the output is X and Y. This is the OR gate. These are the inputs. This is the output. It is X or Y. Okay, this is X or Y. Z is equal to X or Y. Something has mixed up here. Okay, Z is equal to X or Y. This is the NOT gate. So Z is equal to X bar, the inverted version of X. This is equal to, it's not 5. Then we also talked about that this bubble, basically we said that this is the buffer. I hope you remember the buffer. So the buffer is transparent. It does not change the input. Whatever is at the input, that appears at the output. Okay? And then we said the inverter, when you add a bubble here, so it basically inverts the output. Then we said, so if you add a bubble here, so the output of the AND gate would be inverted, and it would become a NAND gate, not of AND gate. If you add a bubble here or an inverter here, bubble means an inverter, like if you place an inverter in series. Okay, so this is your AND gate, and uh, these are its inputs, say for example, and you place a NOT gate in series. So this becomes a NAND gate. Okay, so we don't represent it like this, we just represent it like this. So this is your standard AND gate, and this whole NOT gate is represented by this single bubble here. Okay, so this is your NAND gate, not of AND gate. Similarly, this is your NOR gate, and this is your similarly we also talked about the exclusive OR gate. So this was our OR gate, and this was our exclusive OR gate. Okay, so we talked about that. Just recall our discussion, and then we added a bubble here, so it became the exclusive NOR gate. Okay, so this is important. These symbols you should know. These are the symbols of gates, logic gates, electronic circuits that are used to implement logic functions. And you should also know the input and outputs, or the representation of these functions in the form of these waveforms, or timing curves, or timing waveforms, or something like that. Okay, so this is how this is one way of representing the behavior of logic functions or any Boolean function. So this is the input X and Y. So see 0 0 0 1 1 0 1 1. Okay, 0 0 0 1 1 0 1 1. Now this low level basically shows you 0 volts as the logic 0, then this is 0 volts logic 0, then plus 5 volts or high voltage as logic 1, then again logic 1 plus 5 volts or high voltage. Similarly, the Y input 0 1 0 1, okay, low high, and then their AND. So the AND would be low as long as one of these inputs is low. So it is here, it's low all up until here, and then when all the inputs are 1, so it becomes 1. Or when both the inputs are 0, only then it is 0 or low. When either of the inputs is 1, so it becomes 1. Okay, and the NOT. So if X is 0, so this is X bar. If X is 0, then it would be 1 1 and then 0 0. For example, if we want to draw Y bar, so Y bar क्या होगा? y बार ये चीज़ होगी, ठीक है। So y बार would be, जब y 0 तो ये 1, जब y 1 तो ये 0, y 0 1, y 1 तो ये 0, ठीक है। Similarly, so this is y bar, y का inverted version, ठीक। Okay, so I hope like you know that this is simple. As an exercise, you can draw the waveforms or timing waveforms for NAND gate. This can be an exercise. Okay, this can be an exercise. Forgive my handwriting. I'm doing it with the mouse pad, so it's very bad. So you can draw the timing waveforms for NAND gate, for NOR gate, for exclusive OR gate, okay, and then the exclusive NOR gate. So this can be an exercise. So you would be able to appreciate the use of this particular form of representing Boolean functions or expressions, okay. Okay, logic diagrams and expressions. So here this is an example. This is some Boolean function, and this function is like this. Now we have not studied Boolean expression in detail, but you should have some idea. Okay, this is a function of x, y, and z, three variables. So if we want to have a truth table for this function, we need to have these three as inputs and all their possible combinations. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. So this is in decimal, this is 0, this is 1, this is 2, this is 3, 4, 5, 6, 7. Okay. So this is how it is. Now what would be the value of this function for this input combination? So what is the function x or y prime and z? Okay. So either x, if either x is 1 or this term is 1, so then the function is 1. So x is 0, okay. So let's look at this one. Y prime is 1, but z is 0. So this is 0, this is 0, 0 or 0 is 0. Now how do we get this one? X is 0. So let us look at this term. Y prime is 1 and z is 1. So 1 and 1 becomes 1 and 0 or 1 becomes 1. So this should be 1. All the cases where x is 1, so those cases are 1. Okay? You don't need to evaluate the other expression. Just the simple fact that x is 1 and it is being ORed with y prime z, so you don't need to calculate y prime z in those cases. Since x is 1, so the output is 1 because the output is x or this thing. Here x is 0, so you have to look at this other expression, and z is 0, y prime, y is 1, so y prime would be 0, so the output here is 0. Here y is 1, y prime would be 0, although z is 1, but since y prime is 0, so 0 and 1 is 0, and 0 or 0 is 0. Okay, so this is how we can create the truth table for this function. Okay, now we can also create a logic diagram for it. So logic, how can you create a logic diagram? So if you look, this function is basically the OR of what? It is the OR of, this is our function f. Okay, it is the OR of x. Say this is our input x, and x is ORed with what? It is ORed with y prime and z. Okay, so we need to calculate uh, something like this. Okay, so say this is y, so this is y, this would be y prime. Here we will have y prime. Okay, and this is z. So here we will have y prime z, and here we will have x or y prime z, x or y prime z. Okay, so this is how you can implement this simple logic function. Okay, this is the equation. Okay, and this is the logic diagram. Okay, this is just an example. Like we can have Boolean equations. We can create truth tables and then logic diagram. So they all describe the same function. This truth table, this expression, Boolean expression, and this logic diagram, they all represent the same thing, but in uh, different ways. And we learn about it. Okay. Now, truth tables are unique. Truth tables are always unique because they list down all the possible combinations of the input variables and the value of the function for all those possible combinations. This expression can be different. We will learn it later. And similarly, this implementation can be different. But this thing is always unique. The truth table is always unique. Okay? So if this can be different and this expression can be different, that means like if this circuit logic diagram can be different, that means you can implement the same function in different ways. Okay, and we learn that. We learn how to represent the same Boolean function in different ways. Okay, that's it for today. I'll upload these video lectures, and I hope you listen to them and you'll understand them. We could not have the Q&A session here today. I hope we will have it in on Thursday in our next session. Until then, Allah Hafiz.